Particle P moving in a straight line passes through a fixed point O at time t equals 0 seconds. So that's telling me x equals 0 when t equals 0. At time t seconds after leaving O, the displacement of the particle is x meters and its velocity is v meters per second, and v is given by this expression here. So we want to find x in terms of t. To get to x from v, we need to integrate. So that's 12e to the 2t minus 48t. So we'll get 12e to the 2t. Remember, the exponential doesn't change and the argument will stay the same here therefore, but we need to divide by the differential at the inside, and then we've got 48t squared over 2 plus some constant. Tidying that, we're going to get 6e to the 2t, take away 24t squared plus a constant. Now we know that x is equal to 0 when t is equal to 0. So 0 is going to be 6e to the 0, which is 6. This will be 0 plus c. So c is equal to negative 6. So we have x is equal to 6e to the 2t. Take away 24t squared. Take away 6. So we want to find the value of t when the acceleration of p is 0. So to get to acceleration from velocity, so velocity is 12e to the 2t, take away 48t, we differentiate. So the acceleration is going to be 12e to the 2t multiplied by the differential at the inside, take away 48, which is going to be 24e to the 2t, take away 48. So if a is equal to 0, that means that e to the 2t must be equal to 2. And we could easily just rearrange this to give us that. So, taking the natural log of both sides, we get 2t is equal to ln 2. So t is equal to half ln 2. Of course, you could have got a calculator value for that. Find the velocity of p when the acceleration is 0, so we want to substitute that back in. So the velocity was 12e to the 2t, take away 48t. So that's going to be 12e to the twice half ln 2, so that's just going to be ln 2, take away 24 ln 2. E to ln 2 is just 2 because they're inverse functions, so that's going to be 24, take away 24 ln 2. I'm sure an equivalent calculator answer would be sufficient there. And indeed, checking the mark scheme, it was.